So since it's 5:30, just an update from what I see in my chat here. So this tutorial is going to be presented by Claire and I. And currently Claire is still waiting for approval to get into the app and start presenting. And since this is a 3-part tutorial, yeah, so since this is a 3-part tutorial and the first part is going to be presented by Claire, then we'll need to be patient and wait that someone can solve the technical issue and allow Claire to enter in the app. Here she is.
Oh, I'm here. Can you guys not hear me? Oh, okay, thank you so much. Oh man, this is the struggles I think with the hybrid environment.
Mm-hmm. Perfect. So I think it's yeah, it's 5:30. So
Okay, well, we'll then get started right away. So thank you all for your patience. We're really excited to be presenting on the impacts of data privacy and equity on public policy. And so I'll be starting us off. I'm Claire McKay Bowen. I am a principal research associate at the Urban Institute. And so this part one is just kind of setting the groundwork, talking about what we mean by public policy, what do we mean by data privacy, what is the intersection of the two together. And this is kind of more framing in the United States because I work in a public policy place that focus on domestic issues, specifically social and economic public policy issues in the United States. But there's a lot of lessons learned that we can learn from the applications in the United States to other places across the globe. So for part one, again, we're going to kind of level set here. So I'm going to start with the question of what is data privacy and confidentiality? What do we mean by that? That's like a huge umbrella. So we're trying to carve out the part that both Nando and I work on, and why is it so important? Well, in the United States, on the first day of office for our president, Biden, he did what is called an executive order. So, kind of putting an initiative that he's calling for all federal agencies and White House offices to work on certain initiatives. This one in particular was advancing racial equity and support for underserved communities. So, basically, it's saying that you want to have equity for all, especially people of color and those who have been historically underserved. And so, what does that mean is that you need better access to data, frankly, to make these kind of public policy decisions. But there's an issue with this kind of like inherent trade-off that you'll hear throughout this whole tutorial is the tension between getting better data quality to make those decision making, but then still preserving the privacy of individuals. And so this is an example I like to go walk through. So there's a news article published late of 2019 by the New York Times, where it was following individuals in a data set. So this data set in particular is cell phone data. It has latitude, longitude, coordinates, has people's personal identifiable information removed, and the time of that location. That's all this data set has. And so the New York Times reporters followed one particular individual and found out that this person obviously lived in the Redmond, Washington area in the United States. And that's actually the location for where Microsoft headquarters is. And so they realized like, this person lives in the Redmond area and then obviously works at Microsoft because they're on the Microsoft campus during working hours, and kind of follow this kind of trend of like, well, they obviously live in this area, they work in this area. Then suddenly that person's habit changed going to the Amazon campus. And so like for one afternoon, and then went back to going to Microsoft campus until suddenly regular going to Amazon. And with that, just that those pieces of information, they were able to identify this person as Ben Broly, who at least at the time when this article was published, I don't know where he is now in 2022, but it was heading Amazon Prime Air delivery services. And so some of you might be thinking, well, that's too much information, we shouldn't reveal it. Well, again, I just said earlier, if you recall, there was no personally identified information. The reporters were able to identify this person by figuring out when Ben changed his jobs via LinkedIn. So they used external information to identify the person. Then maybe your follow-up question is, well, we shouldn't release this information at all. That's too much, just not along with time. That's crazy. Well, this information is used by the United States to figure out how to do emergency responses in case of like forest fires and hurricanes. And again, this is a global audience, so some of you might not be aware of that this is historically one of the worst forest fire seasons ever in the United States. And last year we had one of the worst hurricane seasons, and it's projected to have just as severe a hurricane season again. So that's what that information is needed, and the fact that we've been experiencing a pandemic. So one of the reasons I'm not in Korea is I was concerned about the COVID-19 pandemic and whether or not the United States was going to change some of the rules with allowing people to go in and out of the country. And so there was this lack of public data that hampered our ability in the United States to battle the COVID-19 or even do contact tracing, which everyone kept saying, let's do contact tracing. This is the way to fight COVID-19. But in order to do that, we need access to that data that I just said revealed a lot of personal or could potentially involve a lot of personal information. And this also happened in early in 2021, trying to figure out how to roll out the vaccines in the United States. There was, again, not enough data to figure out how to equitably distribute the number of vaccines to certain states in the US. And this was particularly difficult because we already found out that those who are underrepresented were more impacted by COVID-19. And so if we had access to more racial and ethnic data, we could have been like, oh, so these states need to have more vaccines because they've been more inversely impacted by the pandemic. But again, don't have access to that data. So then how can we get access to that? How can we change this paradigm? Well, we need to first figure out exactly how public policymakers in general usually gain access to confidential data in the United States. And so this is kind of the diagram I like to go through when explaining to people about data access. You have this kind of data user layer where people have said, hey, I need access to this data. I need this for public policy making. These are the kind of analyses I need to do. And so they basically are talking with privacy experts, which was Nando and I, saying like, okay, you want these analyses? Well, let me go work then with the data curator or the person who's ultimately in charge of the data. So this could be a federal official who collects that information. It could be like the cell phone provider who has the lat long coordinates that we talked about earlier, so on and so forth. So I'm going to refer to this data set as the confidential data. And this is just to clarify that sometimes when we talk about confidential data, it's already the cleaned form. So just for that clarification, it's the clean but sensitive information that we want to share. And so we figure out what are some of the statistics or information we want to highlight to make sure that we do that proper public policy making. And in statistics, which this is the fun thing, I didn't forgot to mention Nando is a computer scientist and I'm a statistician. So we have different terms here. I like to call it statistical disclosure controller limitations, like some methods of data privacy and confidentiality, ways to alter the data in a safe manner such that you can get access to the data. So he might be using a different term. Hopefully that won't be too confusing, but letting you know about the scope of the terminology there. So applying what we call statistical disclosure control methods to kind of figure out what the results are. So that could be some summary statistics or some tables that people wanted to see, or getting access to sometimes what is called a public micro data set. So a data set at the record level, but has been altered in a way, again, to preserve the privacy of individuals, but trying to make sure that we highlight certain statistics. So then you're thinking, okay, that paradigm sounds like a great idea. Why isn't these problems all solved? Well, it's really kind of hard to implement this kind of framework to get people access to data. So one of the things is that if you think about just the public data set, you can think that, well, suppose our data is social economic data and the user says, hey, I want access to low income. So that seems like a great idea. If you get the record level data set, perfect. Why doesn't that work out? Well, how do we measure utility or usefulness of the data? Or how do we figure out what's disclosure risk? So already I bet when I told all of you, hey, what is data privacy? Or when I said data privacy, you probably had different ideas of what that meant to you. Everybody has their own sense of risk or what their own measure of utility is. So it's kind of hard to figure out exactly how everyone's going to use the data or what is their, again, measure of risk. So one of the examples I usually give, and hopefully this will be understood internationally, is in the United States, we conduct a census, a big one, every 10 years. And so that is used to figure out how to allocate our budget, our annual budget across the whole nation. It's also figuring out how to appoint certain public policy seats, those who are going to make voting or vote on certain bills or laws, excuse me, in the United States. So it's a very important data set, but then also there's some obscure uses for this data set, such as there is at a smaller geographic level in the United States where apparently there's a place in, it's called Ohio, is one of the states. This one smaller area of Ohio where they use this data to figure out how many restaurant permits to allocate. So Census Bureau, which is what's the entity that does our census in the United States, is not going to care about the restaurant permit. They're going to try to focus on the other ones. And so trying to make sure that your data set is fit for all these different kind of uses is pretty much impossible, and to make it perfect without giving people direct access to that data. So then the other thing is a different way of implementing that framework that I talked about earlier. Is like having some mechanism between the data user and the confidential data. So basically the person can ask a question, it gets queried into the system, and you get a slightly altered result out. So this seems like a great paradigm because then, wait, the data user doesn't have direct access to the data, and because there's some interface in between, and you can get direct answers for your analyses. Well, the other thing is, well, the answer got altered a little bit. So like, how do you determine how much noise should be added? Is 5,000 enough? Or is it too much? Are we adding unnecessary amount of noise to that statistic that could alter a public policy decision? The other thing is, like, people are really smart. They're going to figure out a way to kind of game the system. So how do you kind of figure out people's clever questions? So like limiting the number of queries or questions they might ask that system. So one thing is to, oh, sorry, I was distracted from this side chat. Thought somebody asked a question. So one way somebody could be clever about the system is that they could say, after what is the average income, they could ask like, hey, how much does Claire's income deviate from the average? So then in two questions, my privacy would be violated if the system didn't count for that. So this is again why it's so hard. So what kind of is the workflow that a public policymaker or privacy experts working with those public policymakers and those who are the data stewards, trying to make sure that, again, trying to get the proper access to data, but it's not quite a perfect system. So in general, what is that workflow, and trying to figure this out? Well, first thing is you have to figure out what those thresholds of disclosure, risk, and utility. So that again goes back to the whole earlier problem of what do we mean by disclosure risk or data privacy, and what do we mean by usefulness? And you're trying to set that, which can be really hard because sometimes the laws that are in place for whatever country that you're in can be a little bit too vague and not very specific for the technology you're trying to do. So that gets a little tricky, but that's usually step one. Step two is always removing the personally identified information, or PIIs. So that includes people's names. In the United States, we have an identifier called the Social Security number, which is very sensitive. So you try to remove that. There are some also geographic indicators that we have in the United States that we tend to remove. I'm sure in a lot of other countries too, that are a little too specific. So you try to remove those as well. But then, so then step three, you're trying to figure out which are the variables or information in the data that you are trying to anonymize, but you want to still preserve in the data set you're releasing or the statistics you are releasing. And this kind of goes into figuring out like prioritization of what's most important to least important, but you still want to include in. Because that becomes very important in developing in the next two steps, which is developing your statistical disclosure control method or data privacy methodology based on your disclosure risk, and then comparing against your utility metrics for figuring out your data quality. And so you can imagine that this process is very iterative. You're going to repeat steps 4 and 5 multiple times and trying to figure out like, well, the disclosure risks are too high, or if the data utility results are too low, you got to shift some things. Well, easier said than done already. And you will hear this from Nando in part 2, which is sometimes it feels like you're holding sand where you're trying to adjust one part of your method to make good quality, but then you find that sand spills out in unexpected ways as you shift your hand with holding that, again, that sand. So that's like my analogy right there. And hopefully that landed for some of you. And then finally, maybe after you figure out perfectly how to cup your hand to hold all the sand in the perfect way, then you can publish the data or the public statistics that you want. And so how are these kind of methods structured? So again, I'm trying to set up Fernando here, who is going to actually go into the more of the details of some of the data privacy methods that do try to help balance that, again, the need for data utility to make those public policy decisions, but protect the privacy of individuals. So you can kind of think of it as 3 parts. So the first part being a pre-processing step. So that's, again, determine the priorities for which statistics to preserve. So that goes back into the whole selecting the variables that I said before. And again, this is really important because you need to figure out at the very beginning, and this is actually talked about being more and more about for data equity, is if you want equity in mind, you have to think of it at the very beginning, not as an afterthought. So this kind of goes again into the pre-processing step of like, what is the priorities, what are the information you want to preserve, and what things needs to get balanced later on, until you get to this kind of privacy step. So it's what is applying a sanitizer or some mechanism or algorithm that is going to alter part of the data, because you're hearing this tension I keep repeating over and over, and you're going to hear it throughout the rest of this tutorial, which is privacy and utility or usefulness of data are at odds to another. You can't have all the privacy and all the utility because they naturally oppose one another. So the more privacy you want, the less usefulness you're going to get, and vice versa. So you kind of have to figure out what is the proper sanitizer you want to apply to this data. And again, Nanda's going to be talking about that in a little bit in the next part, until finally going into what's sometimes called a post-processing step. So that's ensuring that the results of the statistics are consistent with realistic constraints, such as negative population counts. So what do I mean by that? Well, sometimes you have a very small number of people in your data set, and you're trying to say like, hey, there's so many people in one geographic area of your country. And if it's really, really small, and then you add some random noise to that particular system account, you could get a negative value. Well, even though, let's say, mathematically it makes sense because you're like, oh, it's an unbiased value because we add noise that's distributed evenly on, like, let's say, a normal distribution. Well, the thing is, in the reality, you can't have negative number of people in a geographic area. So one of the post-processing steps that could be is setting that negative value to 0, or even setting other values that, even though they might be positive, to also 0, to kind of balance up that bias issue, because that goes again into equity and becomes a very much an open conversation trying to figure out that balance there. And so in general, this is what, like, to wrap it all together, calling it a statistical disclosure control method. And again, that's the term I use because I'm a statistician, but you're going to hear something else from Nando because he's a computer scientist. So you guys are going to learn some fun terminology from different spaces that are all trying to work together in the data privacy and confidentiality space. Okay, so then how are data used for public policy decision making? So this is really important to emphasize on how these kind of methods interact and trying to determine how we make, again, this public policy decision making in the United States. So I have this photo here because it turns out that if you had access to US taxpayer data, so in the United States, we have a huge administrative data set of all taxpayers in the country. And actually an economist got access to that data and was able to figure out that, well, figure out how to, well, excuse me, I'm now getting tongue-tied. Figured out what are the biggest indicators for economic mobility across generations with that data set. And in particular, figured out that elementary school teachers, the quality of them are one of the biggest indicators for economic success, which is really important because we're seeing that with the lack of certain education in certain areas of the country, and that there's been a wider gap between the middle and the higher class of the United States. This is something that we need to really target. But again, you need access to that data, which for that person or this group of economists, they were picked for from a very selective program. And that's not fair. There's some equity issues there. Like, who does get access to that data? Is it have to be the select few who happens to be in these very elite universities of the United States? No, it shouldn't be that way. So trying to figure out how we can use data privacy methods, which is actually a project I'm working on trying to expand that access of the data set using what's called synthetic data or differential privacy, which, again, we're hinting at this. Nanda's going to go in depth, but using that technology so that other economists across the United States can have access, and to find other ways that maybe we can help figure out economic mobility. Another thing about the data sets that it would be really important to access is the education data, because that determines school district boundaries. So in the United States, education data and census data actually is used to figure out how to draw lines for which schools will be in for certain districts. And so this is actually a screenshot from a report. It's kind of like fuzzy here because it was actually an interactive feature at the Urban Institute showing that how you draw school districts really affect, again, economic outcomes and social economic outcomes, excuse me, for individuals, because it turns out that some people have used data improperly to make this divide the segregation of certain underrepresented individuals. And so in order to prevent that, you again need better access to data. And so how do we figure that out? With data privacy methods. And then finally, I was hinting at this over and over again, how important is the 20, or in this case, the 2020 census is the last big census that we did in the United States, because again, we do it every 10 years. And this is what the data that figure out for us, it's allocating $1.5 trillion budget. I don't know how to convert that for Korean dollars. Maybe I should be better about that because my mother is actually in Korea. So that's a lot of money. Hopefully you can figure out the conversion. In the United States, we have some congressional seats. This is very important for, again, voting for certain kind of laws in place. So it's apportioning 435 seats. That's a lot of seats. It's also planning for natural disasters. I mentioned that before, kind of using that data to figure out how do we do, I said with cell phone data, but cell phone data is paired with census data to figure out how to do those emergency evacuations. So again, for the forest fires and hurricane responses. Again, understanding economic well-being, because I just mentioned before, it is paired with education data to figure out the school districting lines and figure out funding for the schools districts. And finally, that one hint I told you about with that one area of Ohio, which is a state in the United States, determine the number of restaurant permits. So it's very wide ranging of like what people use the census data, and how the impact of releasing that information is determined by using some of these data privacy methodology methods. So with that, I think I stayed under the time, Nando, and gave you plenty of time for your part, right?
Oh, yes, definitely. So thank you, Claire. So I'm going to share my screen and take the control from here.
Okay, let's see. Stop sharing. There you go.
Perfect. So just to introduce myself, my full name is Ferdinando Fioretto. People call me Nando. I'm an assistant professor at Syracuse University, and one of my area of research is study the intersection between privacy and fairness. And I'm going to go a little bit more into the definitions, more of the technical stuff, essentially, that we have touched upon, and Claire has so beautifully introduced. So I have, if I'm not mistaken, I have opened the floor for questions, and I think everyone can ask a question at this point in time. Unfortunately, I don't think I can hear any voice, even if I would really love to. But please, let's keep this interactive. So if you have any curiosity, just ask a question. I'll try to look at the chat every once in a while, but I'm sure that also Claire can monitor that, and if there's any question, I can try to answer that right away. Okay, so let's get it started with introducing a bit of the definition that we're using here in terms of privacy preserving algorithms. So the notion that we're interested in studying here is that of differential privacy. So this is a notion that is 15 years old, and it has become through the years the de facto standard for protecting privacy or protecting the participation of users into a data set. And so this is a very appealing definition because we are able to bound precisely the risk of re-identification of individuals who are participating into a data set. Essentially, I'm just gonna have one slide explaining differential privacy, as I don't want to focus too much on this notion here, but this talk is really on the implication, the negative, well, on the undesired sometimes effect that we can experience when we are releasing privacy preserving data sets, or when we're doing something with this notion of privacy. But this is actually a much more broader topic that we're discussing here. It doesn't exclusively deal with differential privacy processes on. But the definition tells us that if you're having two instances of a word, D1 and D2, and you happen to live in the word D2, so you have a data set that has all those entries except yours, and in D2, in the word D2, you have the same data set, except that now you're also included in it, then an attacker observing an output of an algorithm which is run on the first word should not be much better off in understanding whether you were inside dataset D1 or D2 if he only observes their output. And so this notion here allow us essentially to bound the risk of re-identify an individual who participates into this data set. So differential privacy has a lot of desirable properties, including, composability, so we can reason about different interactions of a mechanism through a data set, through repeated queries, immunity to post-processing, meaning that after we have released a differentially private output, we can post-process that output. So we can use a function to modify that output, and the guarantees are not going to be altered. The process for establish this definition here, for guaranteeing this notion here, strongly relies on the addition of noise onto the data. So you can imagine to have a data set, you're using a randomizer for adding some noise into this data set. And what this talk is about is to try to understand what are the effects of noise onto the fairness of downstream decision making or learning tasks. And to give you some more concrete examples of what can happen, so this is the Title I Elementary and Secondary Education Act, which is one of the largest US programs offering educational assistance to disadvantaged children. This federal allotment in 2015 alone, it distributed over 6.5 billion through basic grants, and it is divided among qualifying school districts in proportion to a count of children that fall in that district, who also have certain properties. So they fall, the family in which they live fall below poverty line, or they receive some form of financial aid in that district. And so the allotment essentially is just a distribution of this money, right? Which is a proportion of the number of children which qualify for that amount in that geographical region. And what we are illustrating in this figure here is the expected disparity errors that are arising when we're using privacy-preserving data as input to this allocation problem. So you're changing all those counts here with privacy-preserving version of counts. And those errors here are represented in terms of US dollars misallocation. And this is done across different school districts in New York, ordered by the size. And what we can see here that some school districts may receive substantially less amount of money than warranted, which results in large fairness issues. Moving on to another application, more in machine learning systems. So the effect of amplifying unfairness by using a differentially private process was firstly observed by Bagatsarayan et al., who measured the accuracy of a differentially private process in a gender and age classification task and a sentiment analysis task. And so essentially the group that they have analyzed in such tasks have either lighter or darker skin tones, or they speak standard American English versus African American English for the sentiment analysis task. The sentiment here is that differential privacy affect the accuracy of the minority group more than it affects the accuracy of the majority subgroup. And so this is obviously important because it carries a big societal impact. So the classification error may penalize some groups over other in important determinations, including criminal assessment, hiring, lending, or typically ML classifiers are adopted now. Biased decision can result in disparity regarding allocation of funds, benefits, therapeutic services. And so those observations are now start to be increasingly common, but still the causes, the root reasons why those observations are rising have only recently started receiving some attention. And so it's really the goal of this tutorial, or this part of the tutorial, to try to shed some light of what has happened in the literature, in the recent literature, to really start understanding why such effects here have arisen. And so this is the setting that we are using. So imagine we have a privacy-preserving, you're probably not seeing my pointer. Oh, yes. No. So imagine you have this privacy-preserving version of the data set, and you're using, so this data set here, I'm sorry, this is a data set which contains some sensitive information about the individuals. And what you're doing is using a privacy mechanism, M, to generate a privacy preserving version, X tilde, of this data set, X. And then you're ready to release this data set in the wild. And now we're using this privacy preserving data for some decision-making task, like an allocation problem. Like what we're doing with the census data, what Claire was essentially covering earlier. And what we want to do is to understand the fairness impact onto those decisions. In a second setting, we're studying, so we're having this data set here, feeding it into a learning mechanism. Now we want to render this mechanism, this learning protocol, privacy preserving, which typically means that we're going to alter the parameters of the model. So we're perturbing the parameters of the model such that the output will satisfy differential privacy property. And we want to study the fairness impact over the accuracy of different groups. Okay, so let's get it started. And once again, stop me and ask me a question whenever you have some. So why does disparity arises in the decision-making setting? So this is the setting. The focus is getting a data release mechanism. For the sake of simplicity, we are going to use a mechanism here which simply add unbiased noise to the data. So zero mean distributed noise. And we are going to then use this privacy preserving data set to allocate some resources or to make some decisions. So we're going to start, we're going to study two problems, allocation problem and decision rules. Essentially, allocation problems relate to allocate some resources to some entities, like the motivating problem that I've showed you earlier. And decision rules are nothing else than 0-1 decisions. So you want to make decisions, maybe whether some group of people qualify for some given benefits. And I'm going to give you some specific examples later. The definition of fairness that we have in mind here is essentially relying on the bias. So the bias is telling us what is the expected error that we're doing when we're allocating our resources by using the privacy preserving version of the data with respect to the original non-private allocation. And so fairness for us is really try to understand what is the maximal bias among all the entities in this problem here, right? So in a sense, you can consider this as the effect over the allocation problem due to privacy, right? Okay, so the first result that was studied by Tran et al. Last year in McKay was a quite surprising result. Essentially, what they have observed, what we have observed in this work here was that even if you're using an unbiased differentially private mechanism, so you're simply adding noise, so with an unbiased from an unbiased shape from the original data, what causes unfairness in this downstream decision making is related to the shape of the decision problem. And so in particular, what they study, what this theorem tells us here in a nutshell, is that you can notice that this bias can be approximated by an expression which involves the local curvature of a problem, so the Hessian, and the variance of the noisy inputs. And so fairness can be bounded whenever the local curvature is constant across all entities of the problem. So all the school districts, right, if they have the same local curvature, then you can bound fairness there, because the variance is also constant and bounded there. But this typically, doesn't often arises, and in fact, what's an interesting corollary of this result is that perfect fairness. So when essentially every single entity has the same variance, right, in this process, perfect fairness cannot be achieved whenever this allocation problem is in a non-convex function, which is the vast majority of the example that we have seen in real life allocation problems. And so even if you're adding the simplest mechanism, even if you're using the simplest differentially private mechanism, like adding Laplace noise or Gaussian noise to your data, this will necessarily introduce fairness issues, despite the noise being unbiased. Now, what can we do with this? Well, one of the motivating aspect for developing a theory to explain why bias and unfairness arises is that now that we understand the issue, we can try to solve it. And so, an informal version of a corollary of the previous result is that when the decision-making task is linear, then the upstream mechanism, the upstream differentially private mechanism, is fair, right? And this just comes from linearity of expectation, essentially. And so the issue here is that then, really paying attention that this is not a data-driven issue, but it's the problem fault. And so one of the solutions that has been proposed in the literature is, well, why don't we try to linearize the downstream decision problem? And so given a problem, then we try to derive a linear approximation of it. And there are many, problem-specific, application-specific techniques that we can use. But one of the idea that has been used in the school allocation problem that I discussed earlier is that of releasing some extra data. So this is called redundant release, and this comes at an small amount, small privacy leakage, or by dividing the budget, further, the privacy budget further among entities. So here, the idea, notice that if you look at this problem is essentially a linear function over its input if the denominator was a constant. And so you could release this denominator, which is just a large number, right? It's the sum of over the counts, and add small amount of noise to this denominator, and then the resulting allocation will be a linear function with respect to its input. And this works surprisingly well for this class of function. So here in pink, we have the illustration. So what is the fairness bound computed for different privacy budgets, so the amount of privacy that you want to preserve when you're using the original privacy preserving model and the original problem P, and then the green bars is what happened in terms of fairness when you're using a linear version. So obviously you get no bias, but also the absolute error that you're receiving, it's actually very, very similar to the error that you're receiving with respect to the original problem. So this is really interesting news. The reason why we have also this blue bar here is because one thing that you could do that always avoids to attain bias when you're using an unbiased noisy process is that of essentially first releasing the output. So you first compute this allocation problem here, and then you add noise to the result of this allocation problem. And so obviously this achieves zero bias because the noise is added onto the allocation problem and it's unbiased. But not only you are actually having much more errors, but what happened here is that it's actually much more difficult to reason about the sensitivity of this problem. So actually it's much more difficult to reason about how much noise you need to inject into the outputs of this decision problem. And also, typically, this is not a realistic scenario because we really want to release the data set. And if we are releasing this data set here in the plane, right, the public data, and then you're using this mechanism here and perturb the output of the mechanism, then you are essentially invalidating really the need of devising privacy preserving data. So that's essentially what happens for this particular class of allocation problems. But as I was saying earlier, we were interested also in this class of 0-1 decision problems. And so here, to motivate these classes of problems, let's look at the Voting Rights Act, which provides a body of protections for racial and language minorities. So Section 203 in the United States describes the conditions under which local jurisdiction needs to provide minority language voting assistance during an election. So this coverage here is determined by the census every 5 years, and it was estimated that about 22 million voting age citizens were impacted by these benefits during the 2020 election. So here we're saying that a jurisdiction, I, must provide a language assistance, which include translating all the voting registration, the ballots, and all the instruction in that minority language. If this decision rule, which is set it's given to us by policymakers, essentially, if this decision rule returns true. And so what this decision rule tells us is essentially comparing various properties of these minorities who live in this jurisdiction. So they're looking at the number of people who speak that minority language of interest in this jurisdiction, those that also have limited English proficiency, and those that also have low grade education. And once again, if this formula here returns true, then you need to translate the ballots and everything. And so this figure illustrates the decision error on the y-axis for the Hispanic language sorted by the number of people speaking the language, actually their distance to a given threshold. And those errors are on the true positive, and they are particularly important because misclassification here implies disenfranchising a group of individuals, right, which is extremely important. And so this figure shows that there are significant disparities in decision errors, and that those errors strongly correlate to the distance to a chosen decision boundary. And so let's take a moment to think about this. So what this is telling us is that just because you're living in a jurisdiction that by chance has a number of people that fall close to this arbitrarily set threshold, then you are in a much higher risk of not receiving this benefit, right? So totally arbitrary thing. Okay, so once again, we ask here why those fairness issues are arising. And now the setting here, it's much more complex than the previous setting because this function that we're analyzing is highly discontinuous. So we cannot rely on the assumptions that were used in the previous result. But something that we can do is start analyzing pieces of this function here. And so one of the things that was done in a paper last year was looking at those ratio functions. Kwong et al. Look at these ratios, and there is an interesting example. So you take 3 counties in Texas. All those counties use these ratios, and the ratios are almost indistinguishable. Actually, 2 of them have equal ratio, and you plot them. So you plot those ratios. The blue points are the ratio computed on the true data. The red crosses are the ratio computed over the private data, and this is in expectation, meaning that you're doing many samples and then you're computing this expected value. And what you see here, it's bias, right? So what you see here is that you want this cross here to be exactly on the blue circle, but all what you see here, it's bias, just coming out from this ratio function. And when you spec those numbers, you say, well, this is, they are exactly the same numbers, so why this is happening? And actually, it's trivial what's happening. The numerator and denominator for those counties are very different one another's. And so obviously perturbing a small numerator has a much larger effect than perturbing a very large numerator, right? So those are very intuitive, and those factors are almost immediate, right? There is no surprise when you're seeing this in this fashion here. But then when you're combining them with this type of application, actually, this is extremely significant. Another surprising result that was shown in that same paper was this notion of composability, right, that we would like to have. So as I told you earlier, differential privacy is really cool because it allows you to reason about how to compose a mechanism and still bound essentially the privacy risks that can be computed for the composition of different mechanisms. And so the authors here observed whether something similar could be obtained in terms of bounds of fairness. And so what you do here, you take this formula, so you take those smaller decisions, those are threshold function, right? Whether this ratio here is larger than a value, whether this threshold here is larger than another value, and so on. And you consider them as independent programs, program P1, program P2, and you plot the bias in blue and pink of those 2 programs, and then you plot the composition, so the logical composition of those 2 programs, and then you start observing that the bias of the composition here, it's always larger than each individual component. And so here, what the paper showed is that the logical composition of those two programs that are bounded by alpha-1 and alpha-2 fairness, it's always alpha fair, it's always basically lower bounded by the max of alpha-1 and alpha-2, right? So this is really interesting. And so here, maybe there is a question. Let's see. Oh, so Zoe asks a question. So you mentioned that we were looking at adding error with zero mean, so adding noise, I guess, with zero mean for marginalized group. We're worried about under allocating too. Would it make sense to add noise biased in the direction that would make it more likely for them to be allocated additional resources, if anything? Okay, yeah, so that's a very valid question. So essentially the question is, you're noticing that there is some bias coming from some population, some marginalized population. I'm actually going to shed some more light on what are the characteristics, the underlying characteristics that are affecting this marginalized population. But we have seen earlier that there is some bias coming from these marginalized populations in those examples. So would it make sense to have different privacy budgets, right, for each population? And this might seem like a sensible solution for this particular problem. But remember that here the task is that of releasing a data set, and this data set should be agnostic over the underlying allocation, of the downstream decision problem. So what this means is that this data set here potentially should be able to answer any possible query. And so while we identify a minority population, for this particular task here, for a different task, the minority population might be different. And so this is really difficult, right, to reason about what is the underlying privacy protection that we should attribute to a particular population, so that we are equalizing, right, this notion of bias here. But it's a very, very valid point. But definitely we could study classes of problems that allow us to reason about this, except that then you would provide inequality with respect to the privacy guarantees that you're offering to some individuals. And so in a sense, you're maybe giving much less noise to the individuals that are the minority one. And so that also means that you're preserving less privacy for those individuals. And then we need to think whether this is still equal, right, as type of process. So once again, if you have questions, just drop them in. So to continue, we can now also reason about a type of mitigating solutions that can be applied to such type of problems here. And this is now once again a much more difficult setting than the previous one. So what the others here did was also try to resort to a linearization trick, but this is again a more difficult problem. So what they did was essentially training a linear model to learn over those features, right? The number of individuals that can have limited English proficiency, those that have low education, and so on. So you train a linear model over those features, and then learn, take the parameters of this linear model and use them as a proxy to run this allocation problem here. And so this is shown in the bias, the effect of the bias for this process here is shown with the yellow and green bars. So the lower the better. So you can get actually much better result here. Except that this was done by essentially splitting up the data sets and then running this mechanism over partitions of the data set. It's just a technical aspect here. But once again, there is a mechanism that it's more or less effective for dealing with this. And so this is really interesting to understand that we can have multiple viewpoints for assessing the equity of a given task. All right. So far, just to wrap up what I said, because sometimes it might be a lot to digest. But essentially, all what I said is that the shape of the downstream decision problem, it's important to understand the effects of a privacy-preserving mechanism onto fairness. But Claire was mentioning earlier that releasing the data, it's not all what we do. Typically, once data is released, then we also want to adhere to some properties, right? Some data invariants. And so what typically what we're typically doing is also running a post-processing mechanism that alter this privacy-preserving data so that those invariants are preserved. So to be a bit more specific, take the case of the US Census data. You typically have geographies that, so for instance, you can consider states, and in each state there are counties. And so what you do, you're adding noise for each of those properties here independently in each of those entries. And what you would like is not only that those numbers, so counts of people would be non-negative, but also you would like that the sum of the all the counties constituting a state will be equal to the number of people in that state. This is obviously violated with very high probability because the noise is added independently. And so entities such as the census run versions of this following post-processing. So you try to modify, right, to redistribute the amount of noise to stay as close as possible to the original noisy output, so to satisfy in this case, the linear constraints of the process. And so one of the things that we notice is that we really want the resulting count to be non-negative, right? Otherwise, they don't really make sense. And so let's see what happens when you run this process here. So what we try to do here is just plot some counts by their frequency. So this is the number of times a given count appears in a data set. So there are some numbers that appear more frequently than some others. Then you can start adding Laplace noise to make those counts privacy preserving. And so here we're showing the residual error of those of these noisy counts. And so you can see that well, they have some shape. Essentially, the variance of the error it's equal to on each of those counts here. And then you can do a very simple post-processing step. You simply ensure non-negativity. Or we can do a more complex post-processing that, in addition to ensure non-negativity, also redistributes those counts so that some constraints are satisfied. And now, two things are important to notice here. Firstly, notice how can we reduce the error. And so this is a well-known fact. Typically, post-processing allow us to reduce the error because you're reducing the space of the hypothesis spaces over which you are searching, and you're only searching in this hypothesis, which is that of true data sets that do not have negative counts. So this reduces the error, but also notice how exacerbates the unfairness. So the deviation here of the errors is much smaller than this one here. And so why this is happening? So in long story short, this is happening due to the non-negativity constraints. Those non-negativity constraints are actually pretty ubiquitous. And so in an attempt to quantify how this process happens, in a result at AAAI last year, we showed that essentially you can have an L1 ball that it's centered at your point, so the count that you're releasing, which is a feasible subspace where there is no bias, right? And so what you could do is you can bound the outer region to understand what is the bias over there. And so in an experiment, what you could do is we plot the residual error, so how much error we're doing from a Laplace mechanism in blue and from a post-process Laplace mechanism in orange here for some counties, for two different counties. And then you shift all those counts. So you start adding to every count 5, then you add 15. And you see as you shift, those two distributions start becoming more alike, meaning that what we are doing is essentially reducing the size of this radius, right? Increasing the size of this radius where bias does not arises, and so that the bias progressively disappears. And again, this is very intuitive because if you have a count which is 1,000 and you add noise there, it's much more difficult to generate a negative number. If you have a count which is equal to 2, then it's much more likely that you're going to generate a negative number an application of a privacy-preserving process. And so what this means in practice, well, this means that post-processing reduces the variance of noise differently in different regions. And so region with many subregions, like counties, census block, and so on, will have more variance than region with few subregions. And so this creates situations where counties will be treated fundamentally differently in decision processes. And one of the tests that we did was running this process in Arizona, which has about 2.4 million people and 15 counties, and Texas with about 8.9 million people and 254 counties. And there is a 6.5 difference in variance, which means that the allocation might be greatly different in terms of error, just because one state has more counties than the other. Possible mitigating solutions in this case here, well, we have been advocating that if, in addition to release the privacy-preserving post-process data, you can also release the simple privacy-preserving data, since that's already private, then what you could do is to post-process the output mechanism. So in this case, you post-process the allocation after you have done the allocation with that private data. So that is private data, but that private data is not post-processed. And so here, what happens? We can essentially reduce the errors substantially in this case. Okay, so to sum up, the error in decision processes really comes because of two mechanisms: noise addition and post-processing, right? And the noise addition is affected by the shape of the problem, and post-processing in this very simple decision post-processing that we have used is especially affected by the non-negativity constraints that we're imposing. So we can do some. So any question at this point? All right. So we can do this the same reasoning for learning task as well. And so let's see what happens in this setting. So in this setting, we have some sensitive data. And what we want to do is to allocate, to produce a differentially private mechanism that now outputs privacy-preserving, outputs, and we want to study the accuracy, the disparity in accuracy about those two different groups or n different groups. And here we focus on this notion of excessive risk, which essentially tell us how much is the differences in losses, so the differences in accuracy due to privacy. So you're taking the private model and you're checking what is the loss of that private model, and you're comparing it with respect to the loss of the original model. And you're doing this for every different subgroup. And so one of the results that you can show here in a kind of warm-up exercise is that if you're using output perturbation, which is really something, one of the most easiest mechanism that you could use in empirical risk minimization, you're essentially perturbing the output of, say, a logistic regression process. What you can do is essentially doing an analysis that is very similar to the analysis that was done in the decision-making process. And you show that output perturbation introduces unfairness whenever local curvature associated with the loss function of different groups is substantially different from one another. And the interesting aspect here, so this is this effect is illustrated, for example, in this plot where you're looking at the trace of the hashing for one group and of the other group, which are representation of the local curvature for those problems. And you can see that this high difference in their local curvature also reflects in high differences of excessive risks. And this difference attenuates as the privacy, the privacy budget that we're using increases. And this is because there is this dependency here between the noise that you're adding and the differences in those local curvatures. But there is a really, I think, interesting point here, is that in processes, such as linear models with L2 loss function, what can happen is that the pure fairness might be achieved by normalizing the input value for each group independently. And this is because the input norms, right? So the input feature of each group directly induces a term that affects this local curvature. And so this is very interesting because, you know, if you think about that, means that maybe individuals with higher salary, they might be affected more or less than individual with lower salary, right? This is what it says. Now, there's also a study on stochastic gradient descent with differential privacy. So essentially, the study of differential of DP SDG contrasts with output perturbation, because here you don't restrict focus on convex loss functions, and the privacy analysis does not require optimality of the model. So this is a much more general and appealing framework. And so in a nutshell, what DP-SGD does is, at every step, you compute the gradients for each data sample in a random mini batch. Then you're clipping the L2 norms of those gradients in a ball of size C. You add noise from normal distribution to ensure privacy, and then you average the gradients, and then you update and you proceed, and you iteratively do this. And so what it has been shown last year in EURIPS is that this process here is biased essentially for two reasons: this clipping and the noise addition. So essentially, the excessive risk definition that I showed you earlier can be decomposed by a term which just includes the non-private loss function, and then a term that it's the private term due to clipping, and a term which is the private term due to noise. So when you're adding them together, you get the excessive risk. And so to understand, you know, why clipping causes unfairness, this is kind of intuitive, because, you know, clipping essentially takes a gradient and removes some information, right? And so the smaller the clipping value, and the more information you're removing. But essentially what happened is that if one group produces updates with gradient norms which are smaller than the clipping value, and another group produces gradient norms which are larger than the clipping value, so you can see the disparate effects, because we're removing some information to one group and we're not removing information to the other group, right? And this is highly likely in scenario where you're about to converge to the loss for one group while you're still not converging for the other group. So the figure here shows the impact of gradient clipping to the gradient norms and to the excessive risk. And also, you know, why, once again, this observation recognizes that the differences in input norms is a crucial proxy to unfairness. The other excessive risk term, which was shown to essentially add, you know, to characterize unfairness, was that of adding noise. And so here, essentially, what we can say is that this term here, it's largely related with the value of the Hessian of a group. And the interesting aspect is that this Hessian, it's closely related to the closeness, to the proximity to a decision boundary. And so what you can see here is in this figure is the correlation between the trace of a Hessian with the closeness to the boundary, right? So in blue here. And so as you can see that there is a very, very high correlation. And what this means is that so the samples which are close to the decision boundary are less robust to noise, and so they can change their final classification just given the noise that you have inputted on the mechanism, and thus you are creating unfairness in that sense in the accuracy. So there's also a possible mitigating solution that has been presented, which essentially relies on a way to add a penalizer to the loss function, which try to equalize those factors which are affecting the excessive risk. And yeah, this plot is just showing that when you're not using it and when you're using it, so you can reduce this excessive risk, right? So ideally, you want the excessive risk to be zero for all groups, so that you do not introduce any bias. All right, so this wrap up part 2. And so in part 3, I think I have the first one. So both I and Claire are going to present jointly this part here. What we want to do is to essentially discuss what are the open questions and challenges that the scientific community still faces, the scientific and the policy making makers are still facing to implement methods which can derive provable fairness guarantees, as well as many more intricate actually questions. So some of the questions that I believe are interesting from a technical standpoint are that we should be better in devising mitigation strategy for data release mechanisms that can take into account both fairness and utility. So far we ostensibly been looking at optimizing utility, right, when we're looking at a data analysis task. But if we are not taking fairness into the equation, so if that doesn't become a factor for over which to optimize for, then it becomes really, really difficult to understand how to obtain a process which is fair. And so I think that that's, for me, a really important point. We might also focus on deriving more general tools for analyzing fairness in classes for decision problems. So you see why it is important to derive theoretical analysis here, because essentially those tools allow us to devise solutions, right, to those issues. And I think that the current work has simply scratched the surface, but there is really a need for expanding this side of research. We have no understanding yet, or we have little understanding of compositional rules for fairness analysis. Also, how to analyze fairness on more complex post-processing steps, like those that are using the US Census Bureau algorithm. And this is extremely difficult. As well as it has been repeatedly observed that privacy and robustness have this interconnected role, and so study that link under a fairness lens would be a really interesting challenge.
Okay. Yeah, it's my turn now. So we're talking about now, like, one of the other challenges is that what are kind of the social inequity risks. So next slide, please. So this is another screenshot of a different article from the New York Times. It was early 2020 about how some of the changes to the census can make small towns disappear. And so for additional context, again, this is going back to the 2020 census being done in the United States. And there was a big shift between the 2010 methodology to protect the privacy of respondents versus the 2020, and that shift being using differential privacy. And so this article was written by people who, one of them is what we call a demographer, who said that, hey, these changes are going to kind of wipe out these towns because they're underrepresented, they're rural, so it's small counts. And so because to protect the privacy of those individuals, you're altering them quite a bit, which is the point of the article was saying this is more disastrous than using the older methods. Now, this kind of brings up a few issues that go honing in on those social and equity parts, which is one is the communication. So this is actually something that we're like 2020 census as being a great lessons learned, is that how to communicate these more complex ideas or these complex concepts of data privacy, fairness, and equity to data users. And this because the bigger the gap between some of the methodologies, the more you have to bridge that gap with the communication efforts. And so the past methods were actually more intuitive to explain to people. So a lot of the data users for that particular the 2010 census were like, okay, that makes sense. You're doing these things called swapping individuals, like maybe one person's one area of the United States, you just swap them with another one at a certain kind of rate, randomly swapping people. That makes sense. That's how you protect your privacy. Oh, you're rounding some values, or you're not going to release information at certain geographies. That makes sense. Like those were a combination of those kind of methods were used for the 2010 census, but 2020 used a differentially private method, and then that was very hard for for people to, again, it is a hard concept. Frankly, it took me years to figure out how to wrap my head around differential privacy, how to make my own methods. And so trying to tell some data users who, especially in these rural areas, for context for those who are outside of the United States, I grew up in a town of 3,000 people where the mayor of that town was also the mechanic. So you're trying to tell that person who doesn't have like the analytical skills to be like, hey, there's this new method called differential privacy. Okay, don't worry, everything's fine. And that goes and raise some red flags there. So again, the emphasis here for this trying to make these social or and equitable changes here, you have to be better about communication. And next slide, please. But at the same time, we have to think about equity in mind. So kind of honing in what like Nando said, like you have to define what you mean by fairness, what you mean by equity. And I also mentioned this too in part 1. And so if you don't have those ideas in mind, you're going to have a harder time releasing data. So the reason I have this screenshot here is that during the pandemic, we learned that there was this huge divide in what they call the digital divide, is the term that's commonly heard in the United States, about how not everybody has equal access to the internet or other kind of technologies, because everybody thought everyone has internet access, like that's a common thing, but that's actually not. I live in a rural state currently. It's called New Mexico. As a side note, it is not part of Mexico, guys. It's one of the 50 states. So just like laying that out there. So in New Mexico, there's a lot of Native Americans, and in those tribal areas, they actually don't have access to the internet, and so people were actually sitting in cars next to certain like fast food restaurants to get their Wi-Fi. I'm talking about this because one of the reasons why we actually don't know about this big digital divide is because, again, that access to data. And so if we can think about these equity issues of not just like equal access to data, but also thinking about equity of access to other kind of technologies and having that in place before we even start trying to release this data, we can try to address like multiple equity issues. Now, I've been saying equity over and over again, like, but this is also honing in that there's different types of equity we can think about. Just like Nando said, it was like about fairness, about access to data, about equal privacy protections. There's also thinking about the equity of those who are representative in the data, who might have to have access to that technology, and so on and so forth. Next slide, please. And so I'm kind of wrapping some things up here with this screenshot. So this is actually an article that was released out from the Urban Institute, where I work at, talking about like, why am I being researched again? So this was kind of a call about how certain underrepresented groups get researched over and over and over again without actual outputs. And so I'm talking or bringing this up because we keep hearing under like equity and fairness, like, oh, we need to help these individuals, we need to do these things. And if that's the case, let's make some actionable items about this and actually follow through, because frankly these groups are tired of being researched over and over again and not seeing any of these outcomes coming out at all. Even though we keep saying like these groups are being affected more, we need to do things. Again, we need to actually like walk the walk if we're going to make the talk, right? So just kind of repeating this over and over again, that if we're going to be thinking about equity, we really should be thinking about actionable items and not just thinking of like, well, here's the theory. And so theory tells us this is what we should do best. Well, no, let's actually think of it all through and figure out what's the best way to deploy it as well. So with that, I think this is the last slide. So with that, that's a wrap up of our tutorial. I know we weren't there in Korea, but I think both Nando and I had some like travel restriction issues. And so we weren't able to go after all. At least I was hoping to, because my mother is in Korea. So, but this is our contact info. If you guys have questions later or just want to connect with us, feel free to reach out.
And I just want to mention that we also do have a few minutes for questions. So yeah, if you do have questions, then feel free to ask them, also now. Additionally, we're going to release, I guess we can release the set of slides, the slide deck. So you could probably access them through our websites. we'll try to do a good job in rendering them easy to locate them for you.
I was gonna say we will stick around for a few minutes, but if we don't get any questions, that's fine. The reason I was saying contact us is because sometimes I don't have questions until like hours later.
Yeah, that makes the two of us.
Be like, oh, wait a minute, I should have asked that question.
I also not sure what time is it in Korea right now.
I think it's really dumb early, actually. I'm trying to remember, like, my mom doesn't message me until, like, an
Oh,
hour from now, and I think that's, like, 9 or 8, so I think that's
it's,
another reason the turnout's a little weird, but this is being
yeah,
recorded so people can come back and watch it, yeah.
it's actually 7:44 right now a.m. right now in Korea. So we started at 6 a.m. That's
Okay, so that makes sense when I said, like, my mom usually messages an hour from now.
all right. Well, so if there's no other questions, I guess we can just wrap it up. All right. Well, yeah. Thank you, everybody.
Thank you, everyone. Have a great day. Or morning. Yes.
Bye-bye.
Bye.
Bye, Claire.